let's start. So any questions so far? Yeah, so this time we talk about these extra mathematic about operational functions. So basically function on matrices. Okay, so we talk about how we define some function on matrices. Say, well, a squared, a cube we can define. We can just have we can just multiply the matrices by several times. But if you have a function that's not so straightforward, say if you want to have the exponential of some matrix, then how we do this is we define this as we just do the function on the eigenvalues. And that's also equivalent to you do a Taylor Taylor expansion on your function, and then you get a polynomial expression for your function, and then you can put the same polynomial on your matrix. And then we see there are three very important operators that we are going to use a lot today. Okay. And so there are these Rx or Rx matrix, Ry matrix, and Rz matrix. And they all are parameterized by the parameter theta. So this will be rotation around x-axis and y-axis. Rotation around x-axis, y-axis, and z-axis on the block sphere. All those three are one-dimensional. All those three are one-dimensional. Not one-dimensional. Two-dimensional, 2x2 matrices, and they work on 1 qubit. Okay, so I want to say 1 qubit. And yeah, so they are really pretty physical because they are rotation. So say in the very beginning we're talking about Stern-Gerlach experiment. So there are so we say this block sphere actually corresponding to your spin in some direction. And then you can think about you physically rotate that spin around x-axis, y-axis, z-axis. Then this is what will happen. Okay, so yeah, so we have those three rotation operators. Okay, Rx, Ry, Rz, and they can be written as this kind of Euler formula with respect to identity matrix and poly matrices. Okay, and as we said, they are really rotation on block sphere, and so you can have this rotation identity. So R alpha, R beta equal to R alpha plus beta. So rotated with angle alpha, rotated with angle beta equal to rotate when you have the same axis, angle alpha plus beta, etc. Okay, and yeah, it's on block sphere. Then the thing probably you care most about, I decided that the midterm will be just whatever I talk about in Monday. So this is the end of the scope of a midterm. And yeah, but we're going to talk something a bit more today. Okay. And so basically today we are going to talk about quantum universality. Okay, so let's step by step. So let's first try to decompose our gates into smaller parts. And the first thing we do is we are going to decompose arbitrary single qubit gate into the Rx, Ry, Rz we will talk about. Well, here we only use Ry and Rz, but X, Y, Z are pretty symmetric, so you can pick any two of the three axes here. Okay. But anyway, we have this Z1 decomposition of a single qubit and unitary. And the theorem says that you have whatever single qubit unitary, so whatever unitary, whatever this 2x2 unitary, and then you can write it as basically a rotation around Z with some angle, then a rotation around Y with some angle, and then another rotation around Z with another angle, and global phase. So it is e to the I alpha is just a phase, and it's multiplying on everything, so this is a global phase. Okay. So yeah, so the most essential part is this beta alpha, beta gamma delta. And the proof is quite annoying, but it's here. I think well, let's just go over the idea because it's not too interesting. So you can maybe it's a bit easier to say this other way around. So basically you can just calculate or use this RZ, RY, RZ, RY, RZ thing, okay, with some info with some angle beta gamma delta. Okay, and yeah, because we already know, so let's see once again here. We have what is R1 and RZ. There are those two things. Okay, so you can put your beta, gamma, delta in, and do calculation. You will get this thing. Okay, and yeah, and also this extra e to the I alpha. And the only thing to show here is that you need to show every unitary. So any 2 by 2 unitary, you have A, B, C, D here. They must satisfy this form. Okay. And so here you try to constrain your unitary enough, to say that this for real parameter will give you any unitary. Okay. And so unitary has several constraints. So the first column should be also a unit vector. So you have this a squared plus b squared equal to 1, and then say you also have the first row here need to be a unit vector. So c squared plus a squared also equal to 1. Okay. And similarly c squared plus d squared need to 1. Okay, so you have several constraints. And this constraint is basically why we have this sine and cosine here. Okay. So the cosine, sine, cosine here. Those are the amplitude part of the ABCD, and because they have sine and cosine here, they will sum square to 1. Okay, so cosine squared plus sine squared equal to 1. And then you need to check the phases. Okay, and yeah. And the phase also has extra constraints. So first you can pick out a global phase, I think, somewhere. You can pick out a global phase is e to the I alpha, and also we have the first column here and the second column here need to have inner product equal to 0, and this gives you some constraint on the phase here. So so if you think about this as a phase 1, and this thing has phase 2, and phase 3, phase 4, and this equation gives you some relation between those phases. Okay. And yeah, so you have 4 phases here, and you have 1 constraint and 1 global, and then you can express the rest with 2 variables. Okay, so you can express all of them with this beta and delta. Okay, so that's basically what we've done here. Okay. And yeah, this is not too interesting, so hopefully everyone's a bit. So yeah, there's we do kind of counting. So yeah, hopefully the number of independent variable check out. So there are 4 independent variable, and here we have 4 independent real variable, and we start with 4 complex numbers. So actually 8 variables, but we use kind of 1, 2, 3. Okay, so it's a bit confusing. Oh no, yeah. So we start with 8, and we use 1, 2, 3, 4 constraints. So we ended up with 4 here. Okay, so for 8 equal to 4 plus 4, it is the number of variable checked out. Okay, and yeah, so that's our starting point. And anyway, the proof is not too interesting, but we have this result, and we are going to use this to do a lot of things. I guess one more thing we are going to use is to do control unitary. Okay, so this is what we are going to do now. Okay, so with this theorem, we can construct any control unitary from using CNOT gate and single qubit gates. Okay, and I think actually what we get is we can get any controlled unitary with only CNOT and these XYZ rotations. Okay, only YZ rotation. Okay, and but anyway, this is what we do. Okay, so yeah. So first, we need to prove this corollary. Okay, before we doing this control unitary, we start with this thing, and then we stay on 1 qubit. So we have U equal to this decomposition, and we want to have another decomposition. Okay. So we want to have U equal to this weird decomposition where U equal to e to the I alpha ax bx c. Yeah, I guess anyway, yeah, U need to equal to e to the I alpha x bx c. So it's a bit more complicated than this. Okay, so here we only have 3 rotation, but here we have 5 gates. So, but A and B will be kind of like our some combination of RZ and RY, and then we put the X gate in the middle. And so this is a more complicated decomposition, and what we get is we want extra constraint on ABC, because before this RZ decomposition, we need to have a specific beta, gamma, delta. Okay. But here, because we put the X in the middle, we can have the extra guarantee that A times B times C equal to identity gate, okay. And it will be useful later when we control our control inventory. Okay, and but anyway, from the thing we just proved, we have our ZY decomposition of U, so U equal to this RZ, RY, RZ, and then we give explicit construction of ABC here. Okay, so we have beta, gamma, delta here, so we just pick ABC with this delta and beta carefully. So A is this RZ beta, RY gamma over 2, and B is RY minus gamma over 2, RZ minus delta plus beta over 2, and C is RZ delta minus beta over 2. Okay. And yeah, so we give this explicit construction of ABC. Then yeah, then we want to check both of those things to are true. So I want to check ABC equal to 1 and AX, BX, C equal to, well, back to this RZ, RY, RZ. Okay, and yeah. Okay, and I guess ABC equal to 1 is pretty fast to check. So you have ABC. I think it's checked here. So yeah, we need to check those two things. AX, BX, C equal to this thing, and ABC equal to identity. And ABC equal to identity we just check here. So ABC we write out all the rotations, and we see that this choice here will be picked carefully. So say this RY and this RY here will cancel out because they are both Y rotation but with the opposite angle. So when you do this two rotation, it's do rotation of degree 0. Okay, then we have RZ here and RZ here, and those two are, and well, I guess the only RY cancel out, then we are left with just RZ. Then we have RZ beta and this minus delta plus beta over 2, and plus delta minus beta over 2. And so the delta part cancel out and the beta part cancel out. So once again, it's RZ over no angle, so ABC just equal to identity. Okay, and then to do the next calculation is a bit harder, and we need to do we kind of think geometrically. Okay, and then we think about the middle part, what's x, b, x. Okay, so x and b is some rotation around y-axis and the z-axis and x, and remember x. I guess intuitively you can think about it geometrically. So x is a rotation around x, the x angle by pi, and when you rotate the x angle by pi, then what happens is your rotation around y and z will become negated. Okay. So you think about if you do, I guess, if you do some rotation around the axis by some angle, but before you do that, you first swap your z-axis by doing rotation around x by pi. You do a rotation, then you rotate back. Then what happens is you will be still rotating around the angle, but with a negative angle. And to do this exactly, we can see with this small clan, and actually we clan something even stronger. So yeah, so if you have f of y, you sandwich any function of poly y with x, then you get a function with a negative y, and then similarly you sandwich any function of z with x, you get a function with a minus z. Okay, and here the function should really be pretty arbitrary, but for simplicity, let's assume the function is nice and has a polynomial expansion. Okay, so function is some polynomial, some summation n, a n, x will n. Okay. And yeah, so what you do is, well, we say it is a polynomial expansion, and we know what the polynomial apply on sigma x is, polymatrix is, and that's the same polynomial with the polymatrix to some power here. And yeah, and then we here prove with the square tree. Yeah, so this can be used linearity. You can put this x sandwiching x in the middle, so you have some overturns with x y to the n x. And you think about what's x y to the n x. So the first thing is xyx just equal to minus y because xy non-commute. So xy equal to minus x minus yx. And we know x squared equal to identity, so this term is equal to minus y. And if you are sandwiching a string of a very long y with x, then you can insert the x times x in between every y. So because x squared equal to identity, so you have just a whole bunch of xy squared, sorry, xyx, xyx, xy squared x. And you know each one of them is minus y, so this is minus y to the n. And yeah, then you write it back, you see that this is f over minus y. Okay, so yeah, so this is f over minus y, and similarly, because x and z anti-commute, you have this is f over minus z. And so what this tells us is that, yeah, so if you sandwich b with x, then you have ry with negative y, and so x ry sin angle x will be instead of ry you have r negative y, so you basically rotate around negative y axis with this angle, and it will be rotated around y axis with the negative angle. Okay, so yeah, so we spent a lot of time talking about this, but what we need is x sandwiching ry means ry with negative angle, and x sandwiching rz is rz with negative angle. And then it's ax, bx, c. Now we can just have the flipped y here. And once again, you see that everything is sorted out. So a, I think a is this part, and this negated b is this part, and z is this part. And then we can now combine the two ry here. Then this becomes ry of gamma. And we combine two rz here. This is rz of delta. And yeah, so this goes back to exactly our decomposition of u into RZ, RY, and RZ. Okay, so this is just a nicely set up proof. Yeah, so yeah, if you want to, I guess you can also just anyway. Yeah, so this is nicely set up, and obviously you can also try to find the result. You can also try to set those three angles into I guess those 1, 2, 3, 4, 5 angles into other things, into variables, and try to solve for when are those angles will satisfy this equation and this equation, and yeah, it should be some linear equation, and then we'll solve for this. Yep, if you want to control the proof yourself. Okay, and anyway, so we have this proof, and it's nice to know the reversal of angle in the middle. But now finally go back to why we want this corollary is now we want to do arbitrary control unitary. And the arbitrary control unitary is this thing. We want for now it's arbitrary 2-qubit control unitary. I guess it's one control bit and one controlled bit. Okay. One control bit and one target bit. So this is 1 qubit and this is 1 qubit. And what I mean by arbitrary is this u now should be arbitrary. So control on 1 qubit, we want to apply arbitrary unitary u. Okay. In the single qubit unitary u, and we want the control version. And we want to do this with only C naught and single qubit unitary. Okay. And this is where we use our u as this ax, bx, c decomposition. Okay. And yeah, so the exact circuit that we do is here. Okay. So this you do C first, and then C naught, then B, then C naught, and Then we have this alpha part and a part. Okay. And note that this is non-trivial. Okay. So we were saying this e to the I alpha is a global phase, but this is the tricky part of a global phase. Okay. So if you are just applying U, this alpha phase doesn't matter. But if you are applying control U, then the global phase actually matter because you will give a different phase to the 0 and 1 component on your control qubit. Okay, so be careful, the global phase can actually matter if you have a control version of your unitary. Okay, and so we actually need to do something with the global phase, and it's this gate here. So this is basically a rotation around the axis. So it's very like Z, but with the e to the alpha here. So only when this qubit is 1, you will get this e to the alpha phase. Okay, and so we want to check that those two things are true. So when the first qubit is 0, then these two things will not happen because when the first qubit is 0, then C naught is the qubit is 0, then it does nothing. And what happens on the second qubit is you will do C and B and A. So we get this, you get to use this ABC equal to 1. And so ABC equal to identity, sorry, not 1, identity. And so the first qubit is 0, second qubit don't get X on anything. Okay? Because there is no C naught and also ABC equal to 1. And when first qubit is 1, then second qubit is going to act by C, X, B, X, A, and it's exactly this C, X, B, X, A. And also the global phase, the e to the alpha is also exon, so we have the e to the alpha here. Okay. So so this is our proof. This is actually a construction for any arbitrary control unitary by C naught and some rotation around X, Y, Z. Okay, so you can just do rotation around X, Y, Z with arbitrary angle. Then you can do any control. Any single qubit control unitary with one control qubit. Okay, so this is why we want ABC equal to identity and XBXC equal to your unitary. Okay, and then we generalize this model. So we have arbitrary control with only one control. And now we want to generalize to actually arbitrary multi-control. Okay. So first we do some definition. So this is the end result we want to get, but we don't quite get it here yet. We'll start with 2, then we'll go to many. Okay. But first we have this notation. So Cn to the U is unitary controlled by n qubits. So here, say we have C4 of U, so it's a unitary controlled by 4 qubits. But I guess a bit of comment here, so you can kind of see that all our notation for those multi-qubit gates are not very precise because we never say what are the control qubit and what are the target qubit. So, but to write down who are the control and target is very cumbersome. So usually we just write down this lazy notation and be a bit ambiguous about what qubits are control and what registers are control and what registers are target. And hopefully it's clear from most of our context. But anyway, so we have this Cn to a U, and then Cn U to a U apply n control qubit and one target qubit. Okay, so assuming those first n qubit are control and there's a few qubit are target, and you will be the control qubit doesn't change. And here x1 to xn assume on a computational basis. I guess we didn't say. And so here, just like before, we assume this x1. We assume this thing is in computational basis. And what happens is you apply U only when x1 to xn are all equal to 1. And here we write with this a bit confusing notation, so we write x1, x2 to xn, and this actually means x1 times x2 times all the way to xn. And this is another bit string x1, x2 to xn. So this is another confusing notation. So multiplication of several bits looks like same as a bit string. But here we mean that this is actually a number. This is x1 times x2 times xn. And all this notation want to say is you apply u only when all the x's are 1. Okay, so otherwise you have a u to a 0 equal to identity. Oh, I guess this is something we didn't prove. We claim that, so recall that u to a 0 equal to identity. And this is something you can prove from our definition of a matrix function. Try to go back. Yeah. So from the definition of a matrix function, you can easily prove that you have any matrix, any diagonalizable matrix, and to the 0th power, and it becomes the identity matrix. Okay. So back to our control qubit, and here is just a notation. So Cn to the u is u controlled by n qubit, and now let's first control C2 to the u. Sorry, C2u. No, C2 to is u controlled by n qubit, and let's first show we can do u controlled by 2 qubit. So for any u, we can control this from C0 and all the single qubit unitaries. Okay, so any u, we can control C2u from C0 and the single qubit unitary. And once again, we get the exact construction here. And first, we need to have a H1 notation. So we need to find a unitary that is basically the square root of u. And it's easy to show that this thing always exists. Actually, there are multiple v that satisfy this, but only need one of them. Okay, so let's assume v is one of the square root of u. So v squared equal to u. Then this control u will equal to just this circuit. So we have control v and the C0, then control v dagger. So v dagger is v is a unitary, so v dagger is actually inverse of u v. And then you also have another C0 and control v. Okay. And to show that this work out, basically you need to check this thing, do the correct thing on all 4 possible values of the first 2 qubits. So there is a 0, 0, it should do nothing, 0, 1 should do nothing, 1, 0, it should do nothing, and 1, 1, it should apply v. And so here we have written down a bit of what happened on 0, 1. So when first qubit is 0 and the second qubit is 1, and because it's 0 on the first qubit, so all the control of first qubit doesn't happen. So this and this doesn't happen, and you have 1 here, and so you have a v and a v dagger here, and v and v dagger they cancel out, so actually nothing happened on the third line. Okay, and let's try something hard. So you have 1 and 1 here, and what happened is everything will happen. So you have control v here and control v here, control v here, and then something funny. So everything happen. That means the middle thing actually doesn't happen. Okay, so because you have 1 here, then you do control v, then because you have this C0, then this becomes 0. Okay, and so because it's 0, then this control v dagger don't actually happen, and then you go to this NOT gate here, then you become 1 again, and then you go back to 1, and let's say you have this control v happen. So you have this control v happen, and this control v happen, and in the result is you have v squared equal to u. Okay, so so this is how you do arbitrary control, the 2 qubit control unitary. And this also means that we can control the gate that we talked before, that's the Toffoli gate. Okay, And yeah, so you can construct Toffoli gate by doing this control square root of x gate. And control square root of x gate is basically a rotation on x-axis by angle pi over 2. But there are other construction people like, so as we will see today, a gate set we like a lot is this HT and the CNA gate set. And you can construct Toffoli from this gate set exactly. Okay. And well, it's this construction is very complicated, but I guess to verify this, I think there are some ways to see this, but the dumbest way to verify this is you really write down the A by A matrix and multiply everything out, and it will work. But yeah, I guess a smarter way is once again you want to verify you have A and B here, and what happened to all the things here, because I guess headma is only on a third qubit, so the A and B analysis should be okay-ish. Okay, because A and B here, and they will stay A and B, just you will get some phase sometime. Okay, and yeah, so this is Toffoli. You can verify it's actually Toffoli gate. Okay, so and it's nice because it comes from this universal gate set of headma T and C naught. Okay, so this is Toffoli, and okay, and then finally we can talk. We can construct. So now with 2, so we go from 1 and 2, and then we go to many. From this 2 qubit controlled unitary, we can actually construct any number of qubit control unitary. So we can implement Cn of u or arbitrary n. And here is the construction. Now this construction is pretty intuitive. So I guess one thing to say is that this is not the most efficient construction. There are much more efficient construction than this, I think. But well, this is easy to understand, and yeah, so this is shown as an example here to show that this is possible. And here we need to do something extra. So for the previous construction, we just have a circuit that do our unitary. But here we need extra workspace. We need to use ancilla here. Okay, so this is different. So so our unitary have control qubit up here. So n qubit, so n actually equal to 5 here, and 1 target qubit here. And we cheat a little bit by saying that we need extra workspace to make this work. So we introduce this ancilla qubit. So and let's start with the 0 state, and they are returned as a 0 state. So they are just used as a middle space for calculation. Okay. And yeah, so what we do is we control on C1 and C2, and do Toffoli on the. Okay, and I guess here we actually only need to do Toffoli instead of general Cn to C2 to a U. But anyway, so we have a Toffoli of C1, C2 to this first ancilla, then Toffoli between C3 and the first ancilla to the second ancilla, and etc. So what happened is at this point, the first ancilla will going to be C1 times C2. So this thing is 1, if only if both C1 and C2 is 1. Because only when both of them are 1, Toffoli is going to flip this qubit. And then similarly, this is 1, this is equal to C1T to C3, because this is 1 if only if C3 is 1 and this point is 1. And this point is 1 if only if C1 and C2 is 1. So this is C1, C2, C3, and so similarly, let's keep this one. And this thing will be C1, C2, C3 all the way to C5. So this will be 1 if only if all 5 of them are 1. Okay. And yeah, so if only if all 5 of them are 1, this control unitary actually happened, and you apply unitary here. And to avoid decoherence between the target qubit, we actually need to reset all the work qubit. So if we don't reset the control qubit, and the work qubit will become entangled when you are not in computational basis state. Okay, because say you start with the control qubit being 0, 0, 0, 0, 0, plus 1, 1, 1, 1, 1. There are too many. 1, 2, 3, 4, 5. Okay, so we start with this state, and you tensor this 0, 0 to the fifth power, and so after you do this, so at the middle point, you will get 0 to the 5 tensor. Because it's all 0, so it stay all 0 here. Tensor 0 to the 5, and plus 1 to the 5, and tensor also 1 to the 5, I think. Yeah, so 1 to the 5 here, and it will be all 1 here. Okay, and this is the entangled state, and so if you just do nothing and throw your work qubit, you are basically measuring, as we say, it's basically measuring the work qubit. Then you will randomly get this 0 to the 5 component or this 1 to the 5 component. But we don't want that. We want a coherent result between the 0 to the 5 and the 1 to the 5. We want 0 to the 5 tensor target qubit doesn't change, plus the 1 to the 5 tensor target qubit get 8 bound unitary. And so what we need to do is we need to uncompute all the ancilla here. Okay? And to uncompute the ancilla, we basically reverse whatever we do here. And yeah, so this will reverse this will reverse that, and it will invert everything, and then ancilla will back to all 0. Okay. And yeah, so this is an important concept. So when you do some operation, you use a workspace. You use a workspace to do some quantum computation. You must clean out your workspace. Your workspace is dirty. Most of the time, you will be entangled to your data space, and that will make your answer not correct. You will not have the correct superposition. Okay, that's an important concept. Okay, okay then. Yeah, we will probably stop today early. Okay, and yeah, let's start talking about. Let's end with this slide and maybe have start a break earlier. Okay, so now we have the tool to talk about universality, and here, like I said, we prove one of the gate set as universal. This is the most popular gate set. Is this C0 Hedman T. So we prove that you only need to be able to do these 3 operation, and then to do any quantum operation. And so first we will prove that if you can do whatever so-called 2-level unitary, then you can do any unitary on any number of qubits. And then we'll prove that you can control any 2-level unitary with this gate set. So C0 and arbitrary single qubit unitary. And this gate set might be pretty familiar because this is a gate set that we use to control those arbitrary control. Because we just talked about from C0 and arbitrary 1 qubit unitary how to do this control, and how to do this 2 qubit control, and how to do multi-qubit control. And yeah, so the middle part is this is the part where that we work very hard to build some basics. Okay. And lastly, we show that to get this arbitrary single qubit unitary, you can just use Hedman T. Okay. And I guess one thing to say here is the last one is approximate, and actually the first 2 are exact. So this is exact. Oh, so this is sorry, wrong key. So this is exact, and this is low exact. Okay. And to make this a bit less confusing, let's first show what's a 2-level unitary before we go into a break. Okay. And yeah, a 2-level unitary is unitary just look like this. Okay, so it's basically an identity gate. So you have a whole bunch of 1 on diagonal and a 0 elsewhere, except on 2 levels. Okay, so on is level I and level J, and so is the i's dimension and the j's dimension on row and i's dimension on i's dimension and the j's dimension on colors. So you have this I coordinate here and the j coordinate here, and on those dimensions, this is it's not this 1001. It's actually like a unitary here. It's A B C D. Okay, and yeah, that's a 2-level unitary. Okay, so you have arbitrary A B C D here, and at all other place, is this diagonal on 1 and 0 elsewhere. So on other place, it's basically identity matrix, and only on those 2 levels is actually arbitrary unitary ABCD. And you can show that for this to be a unitary ABCD, this matrix ABCD needs to be unitary. ABCD is unitary. It's quite easy to show because you just think about what the transformation you have on these 2 things will do on these 2 dimensions. This thing is unitary. Okay, and yeah, so this is a 2-level unitary, and go back a little bit. We have that we are going to prove that 2-level unitary are universal. Okay, this class. So I guess let's take a 10-minute break here, and we'll start with 425. Okay, next class.这礼拜应该不出作业吧？就是有那个 review 用的 ，OK。
应该就是出
个有答案的嘛，就是
对，然后刚好也有3个，其实刚好有3班的。
哦，其实有，哦，其实有，哦，那这个就不用了，就把它拿掉，反正大家已经做过了。
啊，没有，
这个这个没有写吗？
哦，
上礼拜没做，
我已经把功课丢上去了，所以这礼拜就。
哦，这个礼拜本来没有功课 ，OK， 哦，好，所以我们其实有的 ，OK， 好吧，明年要记得把那个丢到前一个礼拜。那我先回答一下。
这个刚刚有个，这个我怎么感觉应该是 C。
我写反了吗？我想想看，应该。
它这边是 A 跟 B， 然后他用这个，他用 A 跟 C 的，他是有点 better 之后，然后他又冒出，而且这边是3。
但那个是，我有点看不太懂。你说我写错吗 ？C square plus B square。你说哪一个是 C？ 我刚刚。哦，你说这个 B 应该是 C 吗？那个 B 看起来的确应该是 C 的样子，对，那是3。但网上写的，我这是复制贴上的，很有问题的。让我想想看，
应该是复制贴上之后忘记改吧？
我想想看，但忘记改的东西好像有点多。A B C D C， 后面好像，好像忘了改很多东西。对，那也是3，但是那应该是cos，对不对？如果它是，我想不对 ，B 跟 C 都是sin，哦，那sin的地方没错。对，那应该是 C， 应该是复制贴上网站，有点混乱。对啊，那我改一下，我注记一下，那个应该是 C。感谢同学认真的看这个。写一下。 怎么了？
这边它是 x， 应该是 poly x， 可是
对，这是 poly x。
为什么还会是一个 c not？
你就一些 two cubic gate 的部分嘛，因为没有这个里在讲，这个是讲 single cubic gate 的 decomposition 嘛，那我们现在要变成是 control 的 version of u 嘛，所以这个 C not 有点像是把这个 x 变成在这两个 qubit 之间把它连起来，所以这个 control C not 是 control x 嘛，所以 control x 就做到了，在这个第一个 qubit 是0的时候它不做 x， 然后在第一个 qubit 是1的时候它在这里做 x 的效果，所以那你就可以让你这个。然后就得到了，如果第一个 qubit 是0的时候，你是 A B C， 然后第二个 qubit 是1的时候，你是 A X B X C， 然后就是我们要的东西这样。
是啊，对，还有就是我刚刚没有听很懂，那 Q level
我用完没打，我应该 upload 这个还没 upload，
这看
对
Q level，
对，
其实我没有听得很懂，怎么看它是一个 Q level unit？
就是它基本上是个 identity matrix， 就是diagonal 是1，然后其他都是0的东西。然后只有在2个 level 的时候不是这样子，就是会选一个 i 跟 j， 就是 di 一个 coordinate，dj 一个 coordinate， 然后 di 一个 coordinate，dj 一个 coordinate。然后在这2个 level 里面，它是有这个 a b c d 的东西。
然后 a b c d 这个本身是有 unit。
对。我没有带下来，在办公室。
我相机跟老师上去办公室吗？
可以啊。就是现在我丢在哪？就是直接，算等一下再给你上去拿好了。我可能会提早下课就是，感觉没有那么多东西可以教了。
现在考古是可以。
对啊，应该可以讲，就是其实不太想给啊，但是既然都在网络上，感觉有人可以找到，那跟他们讲好了。
去那个自修录。
对，就是自修录影。对啊 ，OK。 start. We have our 10-minute break. So yeah. So this is our roadmap for universality. So first we have we need to prove the two-level unitary and universal. And yeah, two-level unitary is really weird thing. It's unitary kind of circuited in these two levels of your big matrix. So think about this is if this is n-cubic unitary, then this will have two to the n different dimension here, and they will have 2 to the n different dimension here. And they will pick two specific dimensions, so dimension I and 2 dimension j, and between those two dimensions you have unitary ABCD. And yeah, and all other dimension the unitary acts as identity. Okay, so this is two-level unitary. And to show that, so first we show two-level unitary are universal. Okay. And we do this by, here we have a typo. Okay. So we do this by, proof by quick idea of the proof here. So let's say we do this on unitary that's just whatever 3x3 unitary. Okay, and so what we do is we want to multiply several two-level unitary and turn this into identity. Okay, so we want to turn equal identity. So first we want to turn this b and c equal to 0. So you can have some u1 such that u1 times u will make this b equal to 0. And what you do is you pick a two-level unitary on this two level. Okay, so u1 will be some two-level unitary that's non-trivial on those two level and identity on the third level. And yeah, you have a and b here, and you pick u1 carefully, and you will make this b 0. Okay. And with all other things change to whatever thing you don't care, you just want the b equal to 0 here. Okay. And then similarly, you make this b1, b0, then you can have another two-level unitary u2 do on those two levels. Okay. So you can have u2 on those two levels to make c also become 0. Okay. So after you do u1, u2, you have this. So you will apply u1 and u2 on u, then you will get this matrix that's yeah, you have u1, u2 on u, then you have this matrix that have 7 whatever coefficients and 0, 0 here. Okay, and then because we know u is unitary, u1 is unitary, and u2 is also unitary, so you have 3 unitary multiplying together is still a unitary. And to have a unitary, so this is a 0, 0, then this must be 1, and this it must be 0, 0. Okay. So this unitary is actually has a back diagonal form, so 1, 0, 0, and another 2 by 2 block here. Okay. And then you can have a u3 on this. You can have u3 on the last 2 dimension to once again turn this f prime to 0, and yeah, so u3 will turn f prime to 0, and then you will get the identity matrix. Okay. So you have u3 u2 u1 u equal to identity. Then you find a way to write u as just a multiplication with two-level unitary. That's u3 dagger times u2 dagger times u1 dagger. And yeah, I guess we didn't prove this, but it's pretty easy to see that the inverse of a two-level unitary is also a two-level unitary and actually on the same level. Okay, because you have this ABCD here, and you have the inverse of ABCD on here, then you will get the inverse of this two-level unitary. Okay. So yeah, so that's the first part. Two-level unitaries are universal. Any question? Okay, so we skip all the dirty calculation here, but hopefully this is okay. I think on the textbook you have actual construction of say A1, U1 here. And once you see a U1, you know how all the other things goes. Okay. And I guess another important thing here to say is so why does this work? Is once you turn, so U1 will first turn is B equal to 0, right? So we say we'll multiply U1, you turn B equal to 0. And the important thing happen here is when you do U2, U2 is applied the first label and the third label, first label, third label. And so you see that U2 doesn't change the second label, and does that make sense? Yeah. I think it's a bit different, but yeah, basically U2 will, how should I say? So basically U2 will do row operation on the first level and the third level, so U2 will not change the 0 here. And so U1 basically do row operation on the first level and second level, so you can make this B0 here. And then U2 do row operation on the first level and the third level, then you make this C0 here. And then you can get A00 here. Okay. And so that's a two-level unitary. And then universal, and then we go to the, I guess, the kind of complicated part. So we want to show two-level unitary from, you can control any of them from C0 and single qubit unitaries. Okay. And so two-level unitary kind of look like this. It's all the ones on diagonal, and except on the ith level and the jth level is this ABCD unitary. I guess I should swap the B and C here. I forgot to swap. Okay, it's ABCD here. We want to do this, and as we said, this U1 with just ABCD is unitary, and it's a single qubit unitary. Okay. And basically we want to start with this U1 ABCD unitary and put it in the correct two levels. Okay. So what we do is we start with actually not the U1 gate, we start with this multi-control version of U1. Okay. So knowing that so U1 is a 1 qubit gate, and suppose our U is n qubit gate. So we want to start with this control control on all other n-1 gate and U1. Okay. And then this is a two-level unitary. So this gate is do nothing when all other qubits are not all 1, and when all other qubits are 1, you do U1. So you have U1 here when all other qubits are 1. Okay, so U1 here. And when all the qubits are 1, and then so basically this is a block diagonal matrix. You have identity on top and U1 here. And remember this is 2 to the n, and this is 2 to the n. Okay. Let's not write this. It's very complicated. Okay. So this is 2 to the n by 2 to the n matrix, and you have a bunch of 1 here. So it's 2 to the n minus 2, and with only the last 2 dimension, you have U1 here. Okay, so this is a two-level unitary, and you just want to swap those 2 dimensions to the dimension I and j here. And there is quite a sophisticated but not too hard way to do this with so-called grid code. Basically, you look up the coordinate number of this ij here. So you have some I and j here, I and j, and here you have this coordinate being this is the coordinate of 11110 and the coordinate 11111. Okay. And yeah, so you want to swap those two things to I and J, and you can do it. And yeah, by so-called gray code. And but for universality, we care about what gate we actually need to use. And the gate we need to use are those C to the n-1x or the multi-control x, or multi-control x or multi-qubit Toffoli. So it's n-1 qubit Toffoli. I guess it's a real way to say it. I guess NB qubit Toffoli. Okay. Or X-gate control on n-1 qubits. And also some X-gate to flip the control of your multi-couplings. Okay, so yeah, so this is how you do it. And here we use, although we use things very little, but we use all the decomposition here. So we use this result to show that we can do this arbitrary many qubit control unitary. And arbitrary many qubit control, in particular, any arbitrary many qubit control Toffoli. Arbitrary many qubit control X. Yeah. So multi-qubit U Toffoli and multi-qubit U. And yeah, multi-qubit U is to get a starting point, and then you have this multi-qubit Toffoli. Yeah. I guess we are going to stop very soon. And then yeah, so this is the first two parts of universal. And lastly, we have the last part of universality. It's any single qubit unitary with we can get them from HEDMA and T-gate. And yeah, so short answer is you can just do this by geometric analysis on Bloch sphere. Yeah. So first, we need to kind of change our basics from HEDMA and T to these two gates. So we think about those two gates, HEDMA T, and T HEDMA, T HEDMA. And they are actually not inverse to each other. And anyway, we say any gate on Bloch sphere is a rotation. So this is a rotation, this is a rotation. And they are actually rotation on different axes. This is you can do explicit calculation about them to check those two facts. So we need two facts about them. So first is there are rotation around different axes. Okay, so just some axis be of some angle. Angle doesn't matter, it's some angle. And also the rotation angle they get here is irrational fraction of a whole circle. Okay. So this is something that that's why we want to swap from H and T to those two things. Because H and T as a rotation is basically a rational rotation, because we know H squared equal to identity, and T, I think T to the is pi over 8. T to the some power, I think is S power is identity. Okay. And yeah, so if you do enough time, you go to identity. But those two gates, they have irrational degree of rotation. Okay, and so then from these things we can show, but just these two properties, we can show that any rotation of Bloch sphere can be getting from them. So first is that you can show because the rotation angle is a irrational fraction. So if you just do the enough times, you can get rotation. So I guess here rotation of any angle. So important part is of any angle, because you have irrational fraction, so you keep doing HT many times. So you have you think about you have say HT to some power, and this thing is never equal to identity, and you actually will become will approximate any angle along the axis you are rotating. And similarly for this TH. Yeah. So you can approximate any rotation around those two axes. And then once you know, you can do arbitrary rotation around two different axes. Then this is some geometric thing you can show. You can show that you can do arbitrary rotation around the sphere by just doing enough rotation around two different axes. Okay. So that completes our proof of the universality. Okay. And I guess yeah, one more thing to say here. And so this is easy to show, but a kind of stupid way to show that everything can be approximated by Han-Hsuan T. And so if you want a more efficient construction to approximate any rotation on your block sphere, it's actually a famous it's actually a famous theorem. It is the so-called Solovay-Kitaev theorem, and here we have a link to Wikipedia. And you will basically do well, it's a more generalization of this, but basically you can show the same thing. Han-Hsuan T will approximate any single cubic unitary, and you will do this with a much shorter sequence of Han-Hsuan T. Okay, and yeah, so I guess that's the end of universality. We do have time to talk about Oracle, but I want to, I guess, but this is a good starting point. Let me see. Okay, I guess let's flash this really quickly. Okay, so this is a flash to the next half of the class. We're going to talk a lot about so-called quantum oracles. And it's a weird way to have input to your problem. Okay, so we're going to, I'm not sure, I guess let's first take a vote here. So how many of you heard about classical oracle for computer science? If you heard about oracle, raise your hand. One of you, okay? Some? Or two? Yeah, okay. And anyway, yeah, I guess we will need to talk about the idea of oracle starting from classical oracle. But yeah, oracle is something that take an input and compute the output. Okay, but it's confusing. Yeah, and but anyway, there I guess we'll have a more detailed explanation here after we have midterm. But basically, quantum oracle is a quantum version of the classical oracle. And classical oracle basically, I guess we should have a classical oracle here. And but basically, classical oracle is something that do this for you. So there is maybe some hard to compute function f of x, and we think about there is a box. Okay, so oracle is also called a black box. So classically, oracle just do this thing. So there is some box that compute the f for you, and you input x, and this will give you output f of x. Okay. And quantum oracle is trying to do this with a quantum gate. Okay. And yeah, to do this with a quantum gate, then you actually need two registers here. So there is a kind of a control register of the oracle and a target register of the oracle. So there is an input register, you take x, and it will stay as x. And there is an output register, you will write f of x as the output here. Okay. And yeah, it will do this thing. And here we guys we are writing this with either version. We assume f of x is 1 bit. Then you have XOR here. And yeah, so one thing you want to say here is that the quantum version of Oracle is much more complicated than the classical version, because the classical version is actually not a quantum gate. Remember, quantum gate needs to be unitary, and in particular, unitary are reversible. So if you just have x go to f of x, then f of x, if this is not a one-to-one function, f of x might have less information about x. So this is not good. You cannot have this as a quantum gate. So quantum version of Oracle will look like this. You have an input, you have the input register and output register, and you will write the result onto the output register in a reversible way. So you have whatever thing you already have on the operator, and you edit it with some f of x. Okay. And yeah, so this is some quick version of quantum error code. And yeah, on the next half of our class, we're going to talk about a lot about quantum algorithms with respect to oracles. Yep. And yeah, we'll save that for after midterm, but go back a little bit. Here we have a very short sketch of how we get quantum universality from Hedema, T, and C-naught. And next Tuesday we will have a review for midterm, and next Thursday will be our midterm. Yeah, so see you on next Tuesday, and we'll start class early today.